What is the impact of errors on the performance of the programmable metasurfaces? Hamidreza Taghvaee here. In my Microsoft project, we try to answer this question by exemplifying the problem for beam steering case. Beyond 5G requirements are high data rate and high reliability. These prompt the research community to look for higher frequencies. In millimeter wave and terahertz regime, the path loss is very high and radiation pattern is very directive. So we need a beam steering system that can provide finer beam control for stable line-of-sight communications. Programmable metasurfaces are among the best candidates for these objectives. In an indoor scenario, we can cover the wall with metasurfaces and provide fast and stable communications. However, programmable metasurfaces as reconfigurable architectures are complex systems. For instance, they are composed of electronic layer, network layer, and electromagnetic layer. Like any other complex system, they are prone to failure. Errors can happen in different layers for diverse reasons. We might have via failure, actuator failure, and chip failure. Let's focus on via failure that can happen for two main reasons: incorrect switching and disconnection. Here you can see a side view of a unit cell design that is performing at 25 GHz. By switching between 4 different capacitances through these 4 different elements, the unit cell has 4 different phase response. Assume that the unit cell is supposed to perform in state 1, but one of the ions switches to a state 2. So in this case, we have 30 degrees of phase error. Here you can see desired configuration of the metasurface for angles of reflection at 45 degrees. You can see by ideal state without any errors, we would have this radiation pattern. But here you can see examples of having faulty unit cells over the metasurface. Faulty unit cells can be distributed over the metasurface randomly, or they might have a specific pattern due to the resource sharing or network architecture. Types of error as another factor might be taken into account. We might have the faulty unit cell might have random values, out-of-state values, deterministic values, and biased values. Let's have a quick overview on the impact of error scenarios on radiation pattern. To this end, we have combined a distribution with a type along with the percentage of faulty unit cell. Cluster stack produces secondary lobe starting at 30 degrees. Clustered bias produces minor lobes. Independent out of state can be tolerated for high ratio of errors. Independent deterministic ends up with a specular reflection starting at 30% at normal direction here and here. If you are interested in this topic, I invite you to read our paper. You will find the details of the methodology, error model, and also the impact of error scenarios on certain performance matrices such as directivity, side lobe level, half-power beamwidth, and target deviation. In the end of the paper, we have provided guidelines for designers. Thank you for watching this video.